this is periodic systems and periodic motion. And I wanted to set it in context. So we're not looking at necessarily deep things of Hamiltonian systems, although they are still sort of there. But we're beginning a new section that's on time periodic systems. Usually this is thought of in terms of systems that have a time periodic force term. Usually it's called forcing. Like if you have a system and you shake it or vibrate it at a fixed frequency, that's called forcing. You could also have forcing by a stochastic time-dependent force. So it's kind of a random signal. But we will focus on a periodic signal. And the simplest case is this sort of square wave that I started talking about last time. And I've just cut and paste from last time where we ended. And this topic is called parametric resonance. If you have a system that has a natural frequency and then you force it, or in this case, like shake the pivot of the pendulum with a frequency that is related to the natural frequency of the system, then you could excite motion that goes unstable. And this, what I like about this is it's simple enough that you can analytically write down the solutions, because we're just looking at a square wave where everything is just theta double dot equals a constant times theta. It just changes what that constant is halfway through. So we know how to solve that. So this is all from last time. We turned this into a map on the phase space. Right, this is the phase space for our system with theta and theta dot. And you start with some initial condition and then look at where it goes after one half cycle and then after the second half cycle. So then this basically tells you what happened over a full cycle. And we can write that map in terms of the initial conditions of theta and theta dot. So the angle and the angular velocity. The way things change is according to a 2x2 matrix. When we combine those two, so the first half of the cycle and the second half of the cycle, we just get a matrix multiplication. We have this overall matrix M. So overall matrix M maps essentially takes the vector of your initial condition and takes it to where it goes after one period. So this is mapping of a vector. So this is a map. We've turned it, our continuous time system, because it's got a square wave representation, becomes a discrete map, where the key thing is this matrix M. We also said this is a stroboscopic map, as it's like you're flashing a strobe light on your system every period, and it's like you're strobing the phase space. So you're looking at where this thing is just every period, and so you'll see a bunch of points. So I ended with saying that if we know some properties of the matrix M, that tells us about solutions of our system. Because not only does M tell us how states map after just one period of forcing, if you wanted to know what happens after n periods of forcing, then the mapping is M raised to the n power times that initial condition vector. And it turns out, it's not really that it turns out, because the pendulum is a Hamiltonian system, even this sort of modified pendulum, it's a Hamiltonian system. So the matrix M is going to be a Hamiltonian type matrix, specifically a symplectic matrix, meaning it satisfies this condition. So we know some things about the matrix M. We know that the determinant of M is 1. And I guess we're not saying this next time, we're saying it now. We're talking about how the matrix M, maybe I'll write it this way. It depends on the amplitude R. It was our amplitude, and X would be the frequency of the forcing compared to the natural frequency. So there's going to be some combinations if we look in the space of amplitude and forcing that will lead to instability and things that will lead to stability. So here's the amplitude and here is the frequency. And there's going to be, we don't know what they look like, but there's going to be regions where you've got unstable motion, meaning if you were to vibrate with that, we vibrate the pivot at that frequency and amplitude will have the oscillations growing so that this kind of gets out of control. And others where it'll be maybe some other region where it is stable, meaning things either stay constant or settle down. So if you shake it at that frequency, in fact, the oscillations of the system you're oscillating will dampen away in some sense. They don't actually dampen, it's just that things don't increase exponentially. Okay. Now, I may have said something before about the properties of matrices that are symplectic. This is a particularly simple one because M is just a 2x2 matrix. And with most things related to stability and instability, we will look at eigenvalues. So because it's a 2x2 matrix, it has two eigenvalues. And here's some properties of those eigenvalues. So I'll write it this way. If lambda is an eigenvalue of M, then there's actually two things that we know. Then so is the complex conjugate, which are called lambda bar. And why is that? That is because since M is real, it's a real matrix. So if lambda is an eigenvalue, then so is its complex conjugate. So if lambda is real, then its complex conjugate is just lambda. You don't get anything. Now there's something else we know, given that M is a symplectic matrix, so it satisfies this. And that is if lambda is an eigenvalue of M, then so is 1 over lambda. Now that's weird. That's unusual. That's since M is a symplectic matrix. And because M just has two eigenvalues, we can only have two different cases. So there's two cases for the eigenspectrum of M. And so we'll say those eigenvalues are lambda 1 and lambda 2. Here is, I guess we'll call it case 1. So let me plot the real and the imaginary axis for the complex plane where the eigenvalues live. And let me include the unit circle because the unit circle plays an important role. If we have a non-real eigenvalue, it actually has to be along the unit circle. So we have lambda and then lambda conjugate, which is also 1 over lambda because the modulus of lambda is 1. Now, why is this? It's because the determinant of M equals 1, and the determinant of a matrix is equal to the sum of its eigenvalues. So determinant of M sorry, not the sum, the product of its eigenvalues. So we have that. So if the magnitude of one of the eigenvalues is 1, then the magnitude of the other is also 1. So that's case 1, and this corresponds to stability. And I'll get to why that is. But let me give the other case. The other case is the real imaginary axis. I got my unit circle there. And if I have a real eigenvalue, and I'll just choose one of the eigenvalues and call it lambda. Well, the complex conjugate doesn't give us anything new, but 1 over lambda does give us something new. So if this is lambda and this lambda is real and greater than 1, then there's going to be the other one, the other eigenvalue, which is 1 over lambda. So in this first case, case 1, we'll say, lambda 1 equals lambda, and then lambda 2 is lambda complex conjugate. Here we've got lambda 1 as lambda, it's real and greater than 0, and lambda 2, sorry, not greater than 0, greater than 1. Greater than 1, and 1 over lambda, just less than 1. This case corresponds to instability. And it has to do with how the eigenvalues are determined, or how they determine how states evolve. If there's a eigenvalue greater than 1, then there's going to be a corresponding eigen direction. Maybe we call it E1. So in the phase space of theta and theta dot, there's some direction. I don't know what it is exactly. Maybe it's this direction. But there's going to be some direction that if you start with a state in that direction, let me color in something purple. Here is lambda. Then the next iterate, so will grow by a factor lambda. And so if lambda is greater than 1, we've got something that's getting further and further away from the origin. The origin in this case is the perfectly downward facing pendulum. And so there's some direction in the phase space that if we start in that direction, we will just keep on growing. So this is what instability looks like. Now, how do we get the eigenvalues? We get the characteristic equation. So the eigenvalues of M given by characteristic equation, which is what? Determinant of lambda times the identity minus M equals 0, which ends up giving us something quadratic in the lambdas. Lambda minus the trace of M times lambda plus determinant of M equals 0. Well, the determinant of M, we know it's lambda 1 times lambda 2, that's equal to 1, because this is a symplectic matrix. About the trace. Trace of any matrix is the sum of the eigenvalues. That's lambda 1 plus lambda 2. So that's our characteristic equation, and this has eigenvalue solutions that we can get explicitly. You have lambda 1 comma 2 is trace of M over 2 plus or minus square root trace of m over 2 squared minus 1. You might, what happened to determinant of m? Well, because determinant of m equals 1, that's already been put in here. So what separates these two cases? Well, if this thing under the square root, if this is less than 0 under the square root, then we're going to have complex conjugate eigenvalues. And that's what gives us stability, that case 1 up here. Otherwise, if the thing under the square root is greater than 1, then we will have, greater than 0, then we'll have case 2, instability. So the criterion for stability is, we'll just rewrite this inequality. It becomes trace of m over 2. That thing squared is less than 1. Okay, and we could just rewrite this. In other words, 1/2, if we just look at the magnitude of the trace. So the absolute value, if 1/2 the absolute value of the trace is less than 1, then you have stability. And that's less than 1. And if this is greater than 1, then you have instability. So because m, and therefore trace of m, depend on the amplitude r and frequency, which we used x, of the forcing, we can say pick a fixed frequency and then look at the boundary between stability and instability for as a function of amplitude. So let's give an example. So for example, suppose we fix the frequency at 0.9 and we want to know what amplitude at that frequency leads to instability. We could figure that out. We could plot 1/2 magnitude of trace of m as a function of r, right, the amplitude. And there's this important dividing line, which is, we're looking at 1/2 trace of m, is it greater or less than 1? And this is just a sketch, I guess. Up here, we've got, it's unstable above that line, and below that line, we have stable. And you can think of it as something's more stable if it's way below that line, and it's more unstable if it's way above that line. But if you were to just plot this, you'll get something like that. There's going to be some kind of critical, for x equals 0.9, there's going to be some critical value of r, some critical amplitude, above which you've got unstable motion. Meaning if I shake the pivot at that frequency with that amplitude or something above that amplitude, then the pendulum will go unstable. Okay. I think I also have I'm using the book Hand and Finch as the reference here, and I think they have a figure for this. I can find it.
What happens at the critical point?
I know someone would always ask that. So I think that's like a marginally stable case. I wouldn't want to be there, but I think technically it's called like marginally stable.
Okay.
It's in the same category. I think that's where the eigenvalues are actually moving along. If you think of it as you're adjusting things, the eigenvalues are moving along the unit circle and they're meeting at 1. So you have a double eigenvalue of 1, which is, I wouldn't trust it. So here's the plot from the book. This is Hand and Finch. Which has a very readable chapter 10. This is their figure 10.4. And they don't even get to the point where like this thing keeps going and probably crosses 1, right? You look at the range here. This changes very little between 0.72 and 0.84 over a range of R from 0 to 1. So you probably have to go to very, very large. What we end up doing is we don't just fix the frequency and then look at a plot of amplitude. We look at both, and then we color code regions where we have instability as a function of X versus R. So just to write that, we typically summarize stability with a plot of, and they call them tongues. They don't necessarily look like tongues, but kind of a long, narrow, squiggly thing. There's tongues of instability in the parameter space. Of frequency versus amplitude. So basically the Rx plane. And this is, in other words, where do we have a resonance response? That's why this is called parametric resonance. So let me give I'll just insert from the book has calculated this. There we go. So this is showing the, oops. This only looks at frequencies from actually about 0.25 up to 1, and then amplitudes from 0 to 2, and regions of instability and stability. So all the shaded regions are unstable, and then everything else is stable. So these shaded regions, these are the regions where we've got magnitude of half the trace is greater than 1. And the boundary curves, so this might be useful. These boundary curves are where it actually equals 1. So if you wanted to get the boundaries, you don't have to kind of compute over a huge grid, you just compute the boundary curves. So these are where 1/2 magnitude of the trace equals 1. And what's significant about this 0.5? 0.5, this means shaking the pendulum at twice its natural frequency. So it's kind of like it's getting something for each swing back and forth. And that's the kind of major tongue of instability. So that is shaking at twice the natural frequency. And then up here, it looks like there's a region kind of around shaking at the natural frequency. And those are the two major tongues of instability. Yeah. So yeah, if just to remind you, R is the amplitude, X is the frequency. So if I made this experimental system and I shook, let's say I shook with frequency of 0.7, I kept changing the amplitude, maybe making it larger and larger and larger. There would come a point where I would reach this boundary, and everything above that, I would see unstable motion, and below that, stable motion. And this is the essence of what a lot of kind of shaking experiments have been, is kind of verifying experimentally these tongues of instability.
Is this also related to the bifurcation we learned at the beginning of the semester?
Like the saddle node bifurcation?
Or the pitchfork bifurcation, yeah.
I don't think so.
Okay.
This is a new phenomenon because we're looking at a time-dependent force.
Mm-hmm. Okay.
Yeah, I don't think it's related to a pitchfork bifurcation. It is a bifurcation because the origin goes from being something stable to something unstable. In fact, let me give you an idea of what stable motion might look like, and I think I have that. Yeah, this is. I mean, this system is actually easy to code up. I was tempted to code it up. You could really easily code this up because we've got M analytically. So let's look at an example of, we'll look at a stable example. And that stable means the origin is stable. The origin is the only fixed point, meaning, you know, if you're downward and you're not moving, you stay downward and not moving. A stable example that's listed in the book, let me show it. Here we go. This is our stable example. So this is actually looking at 0.9 and X, so frequency of 0.9 and amplitude of 0.7. So if I were to sneak up here and kind of find out where it is, it looks really close to being bad. X equals point, R equals 0.7. That looks like it's in the unstable region almost. It is like right here or right there-ish. That's our stable point, strangely. Let me kind of plot it. So that's our stable example. I can give you an unstable example. And well, first, how do we interpret this stable example? This would be like if I started maybe at this point, so if this is my initial condition, then this probably, I'll call that 0. 0 maps maybe over to here. I don't exactly know. So that means that map took me to here, and then this map takes me over to here. You might be like, why are you skipping everyone? I don't know. You don't actually have to go and sequence. We don't know how these vectors are moving. 3, and then this goes to 4, and then this goes to 5, 6, 7, and then, well, I don't know, keeps on going. But it doesn't leave, it doesn't grow. The perturbations don't grow without bound. For the unstable example, they do. So here is, this is pretty awful. So this is showing a nearby initial condition, just slightly changing the frequency. So for the same amplitude, if you can see that, right, this is the same amplitude, 0.7 for both of these, but this has a slightly higher frequency, 0.95, which means now I've moved over to, I'm up here somewhere. So that's our unstable example. Maybe I'll even point these out. Ba-bing and ba-bing right there. So this is showing, it's, if you look over here at what the X and Y axes are, it's kind of 0.6 and below. It's definitely less than 1. Here, things are growing a lot. This says 25 and this says 10. So some initial thing just kept on going and growing and growing and growing. So each iterate, I don't know, this was iterate K, and then here's K plus 1. So after every oscillation, after every forcing cycle, the pendulum is just getting further and further away from that equilibrium point. So is that clear?
I have a question. So
yeah,
are all of the plots like generated by like a square wave of the gravity?
Yeah.
And like,
so it's pretty contrived. It's not real. It's just a simplified example because you can analytically solve it. I'm going to look next at something more realistic where you've got sinusoidal forcing.
Okay, like would it change the graph if it was like a square wave or like the torque input or the motion input?
It might change the graph, but I think qualitatively you'll get the same thing, because what we're calling a change in gravity is just a change in the torque.
Okay.
It's like we've got a certain constant torque for one half of the cycle, and then we slightly adjust that for the second half.
Okay.
So the next approximation that we want to do is to go from this square wave to something smoother, the sinusoid, which is more realistic. Yeah, the next approximation. To go from a square wave, like what's going on there, to a sinusoidal wave. So we will deal with a pivot, and let's say that we're looking at the y coordinate of the pivot, and I will move that according to a periodic function, some amplitude y naught, and then cosine capital omega t. So now this is my amplitude, and omega is my frequency. And I think Hand and Finch gives the derivation. I'm just going to give the answer, which is that our system becomes, our system, meaning our ODEs, become a well-known equation called the Mathieu equation. So Mathieu, this is theta double dot. This is still non-dimensionalized. by the natural frequency of our system. Right, yeah. And it looks like A minus 2Q cosine 2 tau beta equals 0. So this is the equation that's analyzed. And you can see there are 3 parameters here. There's A, there's Q, there's tau. This is a time-dependent linear coefficient for the oscillator, or an oscillator. So this comes from moving the pivot sinusoidally. So my little picture from before of, here's theta for the pendulum. Now we're prescribing, instead of a square wave, kind of an instantaneous thing, we've got y changing as a function of time. And here's theta double dot. We have plus g plus, this is capital Y double dot over L times theta equals 0. Where theta double dot is negative omega squared y naught, the amplitude of the motion, cosine omega t. We define the natural frequency pendulum as omega naught, little omega naught. So that's G over L. We rescale time. The time variable tau, which equals 1/2 gamma times the usual time. And then we get this Mathieu equation. So if you want more details, then you could see it in the book. I'll tell you what these A and Q are. But tau is the non-dimensional time. So this is our non-dimensional time. And what is this theta? Equals 0. And here the over dot equals the derivative with respect to the non-dimensional time. This A is defined as 2 omega naught over capital omega squared, and that's always greater than 0. And Q, which is related to the amplitude of the forcing, this is, with all these rescalings and everything, this is 2 times the actual length of the magnitude of the pivot change, y naught, 2y naught over L. L is the length of the pendulum. And this is also, because they're both lengths, greater than 0. So A, A is like the, it's related to the forcing frequency, because this is where omega shows up. And Q is related to the forcing amplitude, because this is where y naught shows up. So these will kind of be our 2 main parameters related to forcing frequency. And then this is related to the forcing amplitude. And so this equation has been studied. In particular, you could look at these tongues of stability and instability. I guess they're the things that they call tongues are just the tongues of instability. And you do it the same way. So there's the origin, it's theta dot 0 is a fixed point or an equilibrium point. If you map nearby initial conditions over one forcing cycle, you get a matrix M, which is a symplectic matrix, just like the system before. And I don't think I told you what the matrix M is called, but it's called the fundamental matrix solution. It's related to just a linear mapping. We're looking at a linear mapping of what happens to initial conditions in that phase space. What happens to an initial condition, let's call this vector X, and then it gets mapped to M times X, right, over for one cycle. So you could solve for M. M is the, what did I call it? Fundamental. If you were to kind of look up about this, it's called the fundamental matrix solution. Anytime you have a linear ODE, even if there's a time-dependent term, as long as it's periodic and you look at dynamics over that period, you can calculate of the fundamental matrix solution. So M is going to be some matrix. It's going to be a 2x2 matrix. M is just kind of like in the square wave case, it's still symplectic. So you still have those two cases of either two complex conjugate eigenvalues that are along the unit circle, or you've got two eigenvalues that are reciprocals of each other on the real line. And those correspond to the stable and unstable case, respectively, just like before. Often this is done numerically, so you don't solve it analytically the way you could do for that square wave problem. So you numerically can determine, you would calculate M, and then you'd look at 1/2 of the trace of M for a bunch of different values of A and Q. And then you'd look for if it's greater than 1 or less than 1. Actually, what you want to do is you plot the curves where it's equal to 1. Those are the boundary curves of the tongues. And I think I have an example here of a plot. Yeah, this one. I like this one. Okay, go. So here, A, oops. Remember, A is interpreted, it's related to the forcing frequency, and Q is related to the forcing amplitude. And these shaded regions are the tongues of instability. So you see, it looks like most of it is stable. A is related to the frequency, but we have to be careful about how we interpret it. This is the value 1, and this 1, because of how we've scaled things, this is shaking the pivot at you might guess, just like the simpler one, this is shaking it twice the natural frequency. That gives us the largest tongue. So this would be, if I were to plot what's in this tongue, this is the frequency of forcing is twice the natural frequency. We've got this other tongue that kind of emanates from 4. This is actually forcing at the natural frequency. And then up here, this tinier tongue, this is forcing at, you can see things are going down. This is forcing at 2/3 of the natural frequency. And there would be tongues going, you know, higher and higher up. You probably see this pattern. There's something emanating from 1, 4, this is 9, the next one would be 16, and so on. And this is figure 1010 of Hand and Finch, which has a nice write-up on the Mathieu equation. So these would be, we'd call these are the first 3 unstable regions, or unstable tongues. If I had a pendulum, like the way that my hand moves is probably much more like a sinusoid than it is like a square wave. So the Mathieu equation would describe how I am oscillating the pivot a lot better. There are other systems too that can be described by the Mathieu equation. There's also, and maybe I said up here, A is greater than 1. You can kind of do things where A is less than 1, and A less than 1 is interpreted as shaking the inverted pendulum. Sorry, not A less than 1, A less than 0. And let me just kind of zoom in on that region, because this kind of shows a zoom in of, if we were to kind of look at what's happening here and include a chunk of A less than 0, then we would get this picture. And what's interesting about this picture is that there's a region down here where if you oscillate with just the right combination of frequency and amplitude, you can make the inverted pendulum stable. The inverted pendulum is like considered this epitome of instability, right? You've got an upside down pencil that falls over. If you were to shake the pivot with just the right combination, you get stability. So if you shake inverted pendulum just right, you can make it stable. And if I planned ahead, I would have a video of this. I don't know if I planned ahead. Where is it? Let me see if I could get this in here and working. Okay. Yeah, it's called because this phenomenon I think was first seen by a Russian named Kapitza. This is called the Kapitza, some debate over how it's spelled. Kapitza pendulum. And I think it's pretty cool. So let's see if we can bring it up. There it is. Okay. So there's just the normal pendulum. You can kind of see it's not very big. What is that? Like 10 centimeters or something? and they've got this frequency thing over here. I think it says like 58 hertz. They're going to shake that pivot. So they shake the pivot when it's in the downward position and nothing very exciting happens. But they move it up to the inverted position, and whoa, just by shaking the base fast enough. If you see the amplitude, up and down motion isn't very big, but you shake it fast enough and that is stable. That is, that's wild. There was a time that Dr. Woolsey, Craig Woolsey in the Aerospace and Ocean Engineering Department was studying hummingbirds. I don't know if he still is, but he was studying hummingbirds, and he thought maybe the way that hummingbirds stay stable is they're doing this kind of vibration-induced stability. I'm not sure what's happened to that project, but this is kind of at least the first example that I was ever aware of the phenomenon of vibration-induced stability. It is kind of amazing that that can happen. What I've seen, the way I've seen it written is, if you think of this in terms of a potential energy, there's the potential energy, and let's say this is the inverted position there. According to just gravity, the inverted position is a potential energy maximum. So that's, yeah, that's should be unstable. And then somehow vibration adds in a piece that's like very large and can cancel this thing out somehow. So you have some, you can look at, whoa, get a effective potential energy from vibration. Effective potential energy. And then the sum of the two is, gives you like a little region of stability. So as you saw in that video, once the pendulum had moved beyond some certain range, it was stable. So this would be the stable range. So this would be the total, just kind of adding the two. And if you want to know more about the Kapitza pendulum, I could put in a folder about it. If you're looking for a project, you could explain the Kapitza pendulum to us.
I have a question.
Yeah.
What happens if you have like some damping or even like the friction in the pendulum? Like, have anybody looked into that yet?
Well, I mean, the proof is in the experiment, I would think. So that pendulum we saw in the experiment probably has some realistic friction, some frictional torque, and yet it's still stable. I don't see why friction would make it go unstable. If anything, it would just make it more stable. I honestly don't know if people have looked at the mathematical problem of including some friction and seeing what happens.
Okay.
Oh, good question.
I have a question.
Oh, sorry.
Yeah.
What is the function of this kind of shift? I mean, for example, you have like, potential energy shift. So for example, we usually have potential energy, which is in quadratic. And what is the function of this kind of shift, potential energy?
Can you repeat that? I was having a little bit of a hard time.
Oh, okay. So can you hear me?
Yeah.
Okay. Also, my question is, so usually we describe a potential function, a potential energy in a function. So for example, if you're state space, if you have two states, and probably you have potential energy function, which is x squared plus y squared, and what is the function of this kind of shift, this potential energy shift? I mean,
What's the function for this like vibration-induced effective
Yeah.
potential energy?
yeah.
So yeah, so I don't know the details. I could post a paper about it. I think it has to do with you get an effective force by doing an average, kind of let's say our forcing period is capital T. You do an average of that forcing function. And then you could turn that into an effective potential energy due to forcing.
Okay.
So this vibration-induced effective potential energy has to do with you are doing an average, and I think it's over the forcing frequency. Usually this vibration-induced stability is where you've got the forcing frequency is much, much greater than the natural frequency.
Mm-hmm.
So there is some condition for it to work. And so the effect of that force ends up looking like an effective potential energy. And it's kind of like you can add the two. And that's your effective averaged force if you average over time.
Okay. Yeah, it would be nice if you have some materials, some literature about this.
Yeah, I'll post that.
Thank you.
Okay.
So I have two questions actually. So the first one, so in that plot correspond to?
So you faded away there. So you're gonna have to repeat that.
What does A equals 0 correspond to?
A equals 0, I don't know.
Okay.
It might not be a thing. I think it's just A greater than 0 and A less than 0.
All right. And my second question was, is M the fundamental matrix solution? Is that also the state transition matrix?
Yes.
Okay.
It is. Yeah, it's also known as the state transition matrix. It kind of depends on the book. I wanted to mention another place where the Mathieu equation was seen that got me somewhat interested in that. And see, will this work? This is just showing a boat on the high seas that is, it's pitching and rolling. If boats capsize, they typically capsize in roll, like their roll exceeds a certain amount. And the main forcing that's going on is forcing due to waves. So the torque induced by waves. There used to be a professor here who studied this in detail. Her name was Mathieu. She's now at George Mason University. And this video doesn't work, unfortunately, but this was a scale model of a ship in a tow tank, which is very similar to what we have in the basement of Norris Hall. They're actually fixing that tow tank. This is a cargo ship, right? Cargo ships carry millions of dollars, maybe tens of millions of dollars of equipment. And if they roll even a little bit, it could make this happen, where all these shipping containers, many of them probably fell into the sea. And this was due to a parametric resonance from the late 1900s. And you could do there's a 1 degree of freedom description where here phi is the roll. And we're looking at the kind of buoyancy driven self-righting part of the ship, plus the effect of forcing due to waves. And you can study that via the Mathieu equation. So you could do, it ends up being, you could translate it into being the exact same form as this. You just have different interpretations of what A and Q are, but here theta would be the roll of the ship. So some early work looking at criteria for capsize looked at that and found, okay, if you have forcing at a certain frequency compared to the frequency of the ship. If you've ever been in the ship, you probably felt that it rolls at a certain frequency. That's kind of its natural frequency. And then if you have forcing added on top of that, those two things can interact and you could get instability, which is unpleasant to say the least. So the Mathieu, I always forget how to spell Mathieu, even though there's a professor in the department named Mathieu. There's got to be some easy mnemonic. No, there's not. So, but that is it. I thought, well, maybe everything's in alphabetical order, but it's A-I-E-U. Okay. So this is kind of like a first model people will look at if they've got something that looks like a simple harmonic oscillator, but then there is sinusoidal forcing. So such as ship motion and roll due to waves. And what do you know? You're also looking at ship motion in problem 1, the required problem for the homework. This problem does not request that you do the Mathieu equation because we've got all these nonlinear terms as well. Right here, x equals the roll angle, and x double dot would be y dot here. And there's the linear term, negative x, but then we have a quadratic, cubic. We have lots of terms. We even have linear damping and quadratic damping and forcing. So this cannot be analyzed via the Mathieu equation. So this actually asks you to do something more detailed of integrating initial conditions and so on. Yeah. Which is in some sense the next topic. So I've been trying to introduce starting with the last lecture, continuing through here, analyzing periodic systems, meaning there's time periodic systems. We looked first at the square wave and its effect on a pendulum, which just looks like harmonic oscillator with square wave forcing. Simplest thing to analyze. If you look at harmonic oscillator with sinusoidal forcing, that's kind of the next one. More generally, we would look at more general system. And we can use geometry and dynamical systems to do that. So this is the more geometric picture of looking at a mapping of every period of the forcing. Basically, you start with initial conditions and see where they are after one period. And we will look at, you could do this in n dimensions, but we'll look at only 2 dimensions, which corresponds to a 1 degree of freedom system. So we'll analyze things that have this form, x dot equals f of x and t. We're not yet even saying that anything's Hamiltonian. Here, x is R2, so that describes, right, we've got x is x1 and x2. And we've got some special stipulations for what kind of, what f looks like as a vector field. We're going to say that f is, if we've got some point in time t, and then we add capital T, T is our period of the forcing, period of forcing is T, then that is just the same as the force at time T. So T is the, we say it's the minimal period, because right, if I oscillate the pivot 4 times, well, you could say I have a system that has that period. But what is the minimal period? The minimal period is just going up and down once. So we always try to use that. Capital T is the minimal period. So you're like, what is this F of T? F is the vector field. So, you know, F, the vector field, repeats itself every time T. So if I were to, maybe I'll just end with this sketch. Here is the time axis. Let's call this time equal to 0, and I'll sketch out x1 versus x2. So this is like a plane. And in that plane, we've got a vector field. So I don't know, some vectors everywhere. This is my 4x4 grid of interesting vectors. And if we were to look at some intermediate time, say t, little t, less than big T, the vector field will have changed. Let me just plot. Here's like, if we look at 1/2 of the cycle. There's x1 and x2. The vector field will be different, so the vectors will be pointing in different directions. But then once we get back to little t equals capital T, the vector field is exactly the same as it was at the original time. And I'm not going to get this exact, but you get the idea, hopefully. Looks the same. So, same vector field. Which means if we started with some initial condition over here, let's call this X, then evolving in time, it would look like this thing kind of moves to another location. I don't know, here maybe, pierces the surface there, this half time, and then it keeps on going, pierces here. So we would call that X at time capital T. This was X at time 0. X at time capital T, we could view that as a mapping, a Poincare map, if you remember what we did before, but it's, in this case, it's a stroboscopic map, meaning, okay, we're over at this point, we just sort of go back to the first time slice. And so, okay, this is X after time capital T, and then look at how it evolves. In some sense, we've got, we can identify times. And so time is cyclical, since all we really care about is the phase of the forcing. So like maybe this is phase theta equals 0, this is theta equals pi, and this is theta equals 2 pi. Well, then that kind of takes you back here. All you care about is the phase of the forcing. So you can construct a Poincare map or define one, which takes points from the initial time, maps them after a period of the forcing. This thing phi is the flow map of the ODE. x dot equals f of x and t. And then you can analyze that just in terms of the map. So then the map x1, x2, right? We've got some initial point, and then where does it map to p of x, and then maybe where does it map to after 2 periods, p2x. So p of x is kind of like a nonlinear version of the fundamental matrix M. Ooh, I actually like that. P is a nonlinear version of the matrix M. So that instead of M times X, now we've got P operating on X. So our map takes X, takes it to P of X. Whereas before X mapped to M times X, now we've got this nonlinear function. So there are numerical ways to analyze that, and we'll talk about that starting next week.